All right, welcome back, everybody, to conversation number 103. We're going to be talking statistical inference for the ill-informed, or those that just want to be better informed, with Ellie. But before we start, let's thank our sponsors like we love to, because we love our sponsors. We'll start by thanking Conductrix. They've been with us from the very beginning. Thank you, Matt, Nate, Ezekiel, Ashley, and the entire team at Conductrix so much for supporting the TLC. We also want to thank our TLC newsletter sponsors. Again, thank you, Conductrix, Growth Book, and for the first time, we want to thank our brand new sponsor of the TLC, the newsletter, and if you're going to join us at Experimentation Island, you'll get a chance to meet them. Ask Why. So Ask Why just joined us. They've started with the newsletter, and again, they'll be at Experimentation Island, as will Growth Book and Conductrix and a couple of others. So come meet them, learn all about Ask Why, the really cool stuff they're doing. It's pretty awesome. Plus Cat is amazing, and you'll get to hear some of that stuff on the Experimentation Island stage. And of course, thank you, Convert, for sponsoring the amazing Conversations channel and the great way that we can learn about each other and the other data folks and experimenters, UX researchers, and everybody in the TLC every month. Ask and answer questions, get to know each other, and maybe win a little cash. And thank you, Eddie Aguilar and Blazing Growth for sponsoring the TLC community. All right, before introducing Ellie and our topic, one quick announcement and reminder. Experimentation Island. Wednesday, we had our first round of open ticket sales. And if you've been paying attention, you know we've announced a few changes this year. We are the only all-inclusive experimentation conference in the US. So we're really proud of the time that you get to spend with us on the island. We want to make sure you get the most of that time. So we spent a lot of time curating that time, both with amazing speakers, like the first two we announced in the last couple of weeks, June and Jenny. But we also thought, maybe you would like to be a speaker. So this year, one of the changes was we added the very popular speaker competition from our sister conference in Texel. Like Ellie, you've experienced that a speaker competition with Michael Agard. It's pretty popular, and we decided, hey, why not bring that to the US as well? And what it does is it gives an opportunity for people who maybe aren't as well known in the industry, but they would like an opportunity to get speaker coaching from Michael Agard and have an opportunity to get up there and become more well known. And some of the people who went through the speaker competition at our sister conference, the Conversion Hotel, have become some of the industry's most well-known speakers. So it's a really, really great opportunity. So head to the website, read about the competition, and get ready for the next public release, which is October 29th from 1 to 5 p.m. And in the next week or two, we'll also be announcing our next two speakers, which are really exciting. We just confirmed the second one. So I'm pretty excited to tell you all about that. But first, if you haven't met Ellie, you're in for a treat. Probably a laugh. Ellie is pure light, laughter, and joie de vivre, and the very picture of a British dame. She lives and works in the beautiful Salisbury, which I was lucky enough to get to spend time in was it 2 weeks ago? Time is very blurry now. She somehow finds time to lead consulting at Eclipse, an experimentation-focused agency, and educate poor Americans like me on the proper way to eat a scone. She also explained to me the difference between a scone and what I thought was a scone, which it was not. Apparently, there are rules. Jam first, then cream, or was it cream, then jam? It's clotted cream, by the way, not cream.
Anyway. Different counties in the UK have a different.
Yeah.
It's like infighting. It's like how in the States the deep pan pizza versus the thin slice pizza,
right.
but the real regional
But the main
things.
thing is you
like
cannot get enough clotted cream, And I'm so addicted to it now. I literally came home and within a week made my own, and it's now sitting in my fridge, and I'm literally eating it every day. I just had it this morning for breakfast. My waistline thanks you. It's so good. So thank you, Ellie, for that. She brings the same joyful passion to everything she's done. She's spoken to more than 3,000 people in the last year alone, spreading wisdom, laughter, experimentation, insight everywhere she goes. She's been recognized as one of the top 20 must-known CROs 2 years running, listed among the top 59 A/B testing influencers, even took home Agency Experimenter of the Year at the 2022 Experimentation Elite Awards. And in true Ellie fashion, she even made sure I got a Tony's chocolate bar, which I was just showing people. This is amazing. And somehow I have to not eat this. It says test hypothesis, chocolate always converts. It definitely converted me. So please join me in welcoming Ellie. Don't fall, I don't want it to break. The unstoppable, unforgettable, and wonderfully brilliant Ellie. So let me stop share and give you the screen share. Take it away, my friend.
There we go.
Stu says cream then jam.
You should all see something that says TLC, Statistical Inference for the ill-informed.
Yes, ma'am.
And you shouldn't be seeing my presenter notes, hopefully, which have nothing in them, but that's, yeah, good. Awesome. So, this session kind of came from two places. One was some random chats I had with Kelly. And then the other was I ran a session a few weeks ago for actually another agency who asked if someone could do a session on statistics. And I thought, oh, actually, doing all this reading up, I now feel like I might be in a position to like reiterate some of this stuff in a good way. And Kelly did a great job of introducing me, so I won't bother to introduce myself. But if I click through, you can just see a nice little QR code you can scan if you want to connect with me on LinkedIn, if you'd like. So where the other places came from is I spent a lot of time in my past life thinking, I don't know enough about statistics, so I'm going to go and teach myself statistics. So I went away and I started a master's in applied statistics. So I have an undergrad in science, and I was like, I still don't feel like I know enough maths and enough statistics. So I was like, great, I'll go and do this applied statistics master's. And what that taught me was that it's incredibly annoying doing a really theoretical statistics course in a maths department, because they make you do everything longhand. You have to draw everything out. You have to like learn everything properly. And it's really boring and abstract. But doing a stats course through a maths department is incredibly useful because they make you do everything longhand. So there is no way for like the essence of your decision making to hide behind clever words, clever coding, or anything else, they don't use abbreviations, they just write stuff out in full on a chalkboard. So there's no getting away from attempting to learn. And then I also did a data science course. I did them the wrong way around. I did the data science course first, which is what triggered me to do the applied statistics one, which is often data science courses are completely divorced from the statistics that underlie the thing that you're doing. So you don't really learn why you need to use a specific technique. You just learn lots and lots of techniques and how to code them. But actually, because it's divorced, it's incredibly useful because you don't learn why you need to use a specific technique, but instead you learn how to scale it up really fast, and actually means that you can run it really fast. So they kind of serve different purposes. So if any of you are sat there and even remotely considering, I don't know why the first D is not boldified on either of these as well, but if any of you are ever considering doing a course, it is useful, but I think go into it with your eyes wide open about like what you want to get out of it. Like for me, I went and did that applied statistics course because I'd done a data science one. I'd done really well in the data science one, but I was like, but why am I using like a linear regression here, but I'm using a t-test here? Like, why? I don't understand why. And that really irritated me. So that's kind of why I went away and did it. But this session will not teach you how to do stats. I'm not going to make any of you professional statisticians by any stretch of the imagination, not in an hour. And theoretical stuff never trains you how to do something as well as physically doing it and practicing it. Like, think, when you were doing whatever the US equivalent of GCSE or A level is, and you just do those equations over and over and over and over again until you can do them by rote before you go in the exam. Sometimes actually that helps when you're trying to learn this kind of stuff. So the physical act of doing it over and over again, whether it's in code or you're doing it by hand. But this session will potentially make not even make you feel less stressed about stats if you're already stressed about stats, but it will merely show you that everyone else is as stressed as you are. So hopefully that's what everyone will take away from the session. But also a lot of people talk a lot of hokum, a lot of gumph, they use a lot of abbreviations. It's so straight talking. It's a big problem in our industry. And I am constantly hearing people throwing around abbreviations and they sound really cool, and they put some like slightly catty comment on someone's LinkedIn about, well, you should have done it this way. It's like, well, no. there's lots of ways to do everything, so it's actually easier to pick the simplest way to do something or the best way to do something rather than the most complicated. So this session will not teach you how to stat, it'll make show you that everyone else is stressed about it. So don't panic, carry your towel, basically. So what we will cover is a little bit about reasoning and inference. So really stepping back from even thinking about statistics, like what is reasoning and inference? What are some schools of inference? I'm not going to mention the F word and the B word, but I will. How anyone can do complex statistical regression if they just squint? I'll show you that, guys, that with a Slido in a second. Moving from descriptive statistics to hypothesis testing, and if time, we can cover some cool stuff like experimental design, but we will probably run out of time. So I've intentionally made it so the content stops before that. So our industry has a problem. We love making stats and data complicated. We do not love making things simple and accessible. We like to sound clever. Consider this word cloud that Claude AI made for me. So we've got clustering, Cox models, logic models, quantile regression, data visualization, why binary data models are on their own, nobody knows, just blame Claude. All these different types of things that all have some vaguely statistical term behind them. And it's really complicated. And, you know, if you've not had that kind of training and background, you're not necessarily sure which technique is the right one for you and where it comes from, and people bandy things around quite a lot. So really, I want to step back and think about like, what is reasoning and inference? So there's almost like two types of reasoning. Deductive reasoning is when you start with an axiom, like a pre-held idea of how something works. So that's kind of like probability theory and probability distributions. Like we know that the probability of something happening we've got a theoretical hypothetical model for how it will work. We've predefined how a particular distribution will work. So we've deduced how to get there through our own sort of abstract reasoning. Whereas inductive reasoning is like the opposite way around. You're starting from specific data and you're drawing conclusions from a sample. And actually, that's obviously where all of us, when we're doing A/B testing, we tend to sit on that side. So that's where you get inference from, inferential statistics. And there's different schools. I use the word schools. Some people use the word paradigm. I don't like it when people say methods. And I don't like it when people say testing. I don't, frequentist testing, frequentist methods and stuff. They're just, it's like a style. It's like one, I'll come on to this in a bit, but it's like you can do different types of tests within the schools. There's almost like a matrix. It's not all the schools are just one way of doing things, for example. And I've got an analogy for this in a minute. So frequentist, Bayesian, and likelihood. And then just talking very quickly about the difference between descriptive statistics and inferential statistics. So every time you do something in GA4, you're basically doing descriptive statistics. You're plotting the number of times that something happens, the frequency of which something happens over a month. Well, you've just done some descriptive statistics. Yay. When you move into inferential statistics, you're using something like a test statistic, which helps you to judge how extreme your observation is. So let's say you've made all these observations in GA4.
She freeze for everybody else? Yes.
Oh. I can still hear you guys. Am I back?
You're back.
Yeah, sorry. Was
Okay.
I still audible, but just frozen?
No.
No.
You froze.
So where did I freeze?
You said GA4 descriptive, and then you said
halfway through the slide, basically halfway through the slide, because you pulled a funny face. I saw you pull a funny face, which was like,
we're like,
Ellie stopped. So essentially what I was saying in the second half is inferential statistics lets you then infer. So you're basically drawing some sort of conclusion, or you're taking an observation that you've made from that month of data, which was different to all the other months of data. And then you're going to say, oh, is this result unusual? And it lets you say how rare or unusual an observation is using intervals and p-values. So the most common schools of inference that I just mentioned, frequentist, so focuses on how long run frequent, you can run something over a period of time and have an expected frequency, and you want to calculate that kind of likelihood within that frequency over a period of time. It's much more around, I've got a fixed amount of time, I've got a fixed bucket within which I'm operating, versus Bayesian, where it's more around the belief and the analysis of sort of your beliefs. So they're slightly different to each other. And then I mentioned likelihood. Likelihood is partially involved in the other two, but you can do sort of likelihood methods where you're kind of taking a set of parameters that you assume have a probability distribution, and you have some observed data, and then you want to try and get your probability distribution, your model, to fit your observed data, and you use the maximum likelihood function. So if you want to learn about that, I put a note there in the bottom right. And there's also quite a good blog here that I put the reference to, because this guy just did quite a good analysis of both. Let me just skip that, actually. So frequentist based, you've got a parameter of interest. It has a distribution which is unknown but fixed. So parameter of interest could be the mean. It could be something else you're trying to learn about your population, but it's something that you are trying to measure, but its distribution is unknown but fixed. So Larry Wasserman's stuff is very good if you want to learn more about sort of large-scale inference. So in frequentist inference, probabilities are interpreted as long-run frequencies. The goal is to create procedures with long-run frequency guarantees. So that means that your confidence intervals, p-values, and related quantities are statements about the randomness of our sample and estimator, but not theta itself. So I've got a nice example on the right here, where the figure shows like the interval for a specific mean, and in this case the mean was 21.4. The top panel shows the whole distribution of the population, with some arbitrary sort of skewness built in, and then the lower panel shows how the coverage of the different confidence intervals of every single observation, some of them sit within the sort of 95% confidence level that we've set, and a couple of them don't. So that's kind of trying to show you how the observations within frequentist inference are kind of observed, and then how you're measured. But basically, there's something about that you want to learn about, but that the population, there isn't any variability in that theta, that parameter of interest. It's unknown but fixed, which compared to Bayesian it's unknown, but it's treated as a random variable. So that's where people start talking about their kind of prior belief. So to quote the Larry Wasserman quote, in Bayesian inference, probabilities are interpreted as subjective degrees of belief. The goal is to state and analyze your beliefs. So we quantify our uncertainty about theta directly via a probability distribution known as the posterior. Before seeing data, we can also express our prior beliefs about theta using a prior distribution. And then after observing our data, our beliefs are updated and summarized in the posterior distribution. I will come back to Bayesian in a bit, but the idea of the three graphs on the right is like, imagine you just started at a new company and you started an A/B testing program, and you knew nothing about your user data other than what you'd looked at in GA4. You'd not run any A/B tests before. No one had any historical A/B testing on a specific thing. And you had to start testing your first test. You wouldn't have any prior beliefs about where any of the things that you were measuring lay. So you've got no, in that scenario, your prior belief, it would be completely flat. There would be no addition that your prior would be making to your distribution that you're measuring. But imagine that you're in an A/B testing program, you've been there for 2 years, and you've literally run the same A/B test 20 times in a specific area on a specific metric, and you know your site really well. Like when I started at Photobox, I didn't know how certain metrics were going to perform. By the time I finished at Photobox, I could tell you by product how well certain things were going to perform by season, and whether an A/B test would take a long time to run or short time to run, whether I'd be able to identify a lift very easily on a specific metric, on a specific product, on a specific page. So I had this is I'm trying to break it down in an intuitive way, but your prior is kind of like your belief that you come in with. Like you can even map it to your gut feeling about how something's going to work as well, or how your stakeholders feel about something's going to work. And all it does is it narrows the focus of your testing in more deeply in that space. So if the prior is completely flat, you don't narrow in on a specific part of the sort of probability space. When it's not, you're kind of narrowing in on a specific area. So that's the best way that I can describe the difference between the two. Essentially, there isn't much difference when there is, but there isn't. But if your prior is completely flat, you might as well switch to frequentist testing. So, or frequentist inference. There are other reasons to do Bayesian, but we can come back to that when I've got a section on Bayesian later. So an analogy, we're all road users at some point. Some of us drive cars. In the UK, some of us take the bus, some take a bike, and some walk. Some of us choose the method with the most complex rules and instructions that have really clear boundaries of what we are and aren't allowed to do. Some of us choose the method which is the quickest to get to the answer or to get to where we're going. Some choose the method which is most environmentally friendly. I want to take the bus because it's more environmentally friendly. Also, some people are better drivers than others. Some are very bad and unethical. We're on the road and some of us drive on the left and some of us drive on the right. So that's my kind of analogy for thinking about, like, all of us are trying to do data. Some of us are better at it than others. Some of us are a bit unethical in how we present results. Some of us maybe drive on the left, as in we might use one school of inference. Some of us drive on the right. There's nothing specifically better or worse about one or the other. You just need to think about the context that you're in and why you might choose it in that particular context. And obviously, as a pedestrian, you've got the freedom to go everywhere. So you're not bound to specific routes and lanes and stuff. You can cross the road and you can do what you want. So you've got a lot of freedom. So that's kind of the analogy of like different schools of inference and different types of tests. The other thing I wanted to talk about was a little bit about probability distribution. So when I started my stats course, don't be terrified by this diagram, by the way. We got given this on day one, and what it does is it tells you the relationship between all the different probability distributions that you might encounter and their type. So the stuff on the right is basically the one I got given in my stats course. The one on the left is where I found a version where they show the distribution. But most of you, when you've been doing frequentist stats, you'll already be familiar with the normal distribution. Kind of that's what we talk about a lot when we have stats that are coming out of an A/B testing tool. But some of the other distributions that are quite interesting, it's got the normal. You probably might have done chi-squared at school. I had to use the chi-squared test to do limpet measurements to see whether they were taller or fatter at the top of the beach or the bottom of the beach when I was like 16. Students' t-test, which is related to the normal very closely. It's a matter of scale. The Poisson distribution, also very useful. The Poisson distribution is more to do with like how frequently you get an observation is related to the period of time between the observations. So it's the equivalent of you wait half an hour and then see 3 buses sort of measurement. How likely would it be that you would see them evenly throughout the period of time, or would you see them all clustered together? And how many would you be likely to see? Would it be 3, 2, would it be 20? That kind of thing. And then the ones that you can see on the left, which are lines, they're all the ones which are discrete distributions. The other ones are continuous distributions. So those are a few to pick out. But what this is really nice at doing is it gives you the relationships between them. So you understand, oh, actually, these two expressions, these two distributions are very closely related to each other. And I always found that very helpful when I was trying to learn all of these. And both of these diagrams are available online. So I'll see if I can find the links to them and pop them on the chat, because they're kind of freely available for download online and stuff. So and then I also got given this on my first day of my stats course as well, so I won't go through this, but this is like the terrifying, all the parameters and all the things you have to learn, and I was like, so yeah, don't look at those, they're terrifying. But it tells you a little bit about how each function works basically. And then the other thing I wanted to talk about was parametric versus non-parametric tests. So if I actually go back to here, you can see some of them have like a nice normal distribution that's like a curve. So obviously the normal distribution does, the student's t does, and the binomial does pretty much. But you can see some of the others don't follow that neat pattern. So something like the Poisson, the chi-squared, the gamma, the beta, because they're not a nice, pretty, happy, normal distribution, they're what we call non-parametric tests. A non-parametric test can be useful in certain scenarios. If ever you've done, like I said, limpets. I once had to measure the heights and widths of lots of limpets on a beach, and that needed a chi-squared goodness of fit test because you're measuring the difference in ratios rather than the difference in means or the difference in observations, like you would if you were taking conversion rate observations. They can be really useful, and you can apply non-parametric and parametric methods both in frequentist world and Bayesian world. It's a bit rarer to do a non-parametric Bayesian test, but I have found one online. They just said it was very rare and unusual to do it, but you might find yourself doing sort of a Bayesian inference in a world where you would select a specific test method, like an F test or a T test or that kind of thing. So that is sort of what I'm trying to show in terms of there are different types of tests, and the different types of tests have the option of different schools of inference. So it's not just one way or another way. I want to move back quickly to some descriptive statistics that basically hopefully should be something you might have learned when you were like 15 or 16, but have put to the back of your mind out of fear and terror. So here's a little graph, and the expression for the graph on the right, so y equals mx plus c, basically shows that you've got a linear graph, a linear relationship between x and y, and there's a particular rate of change, which is n, and then there's a particular point where it's crossing the y-axis, which is the plus c. So in this instance, I've plotted c equals 0 and m equals 1, so it's literally a one-to-one relationship between y and x. And then you can see in this instance, I've plotted where m equals 2 and c equals 2. So you can see the rate of change is faster and that it's slightly moved away from the 0 point in the graph. So what we're going to do next, sorry everyone, is we're going to have a little quiz where I'm going to ask you all to think. And just remember that it's 5:30 for me on a Friday, so I'm having to think even harder than you. So let's say we've taken some observations. They've come back from a specific experiment that you've run. Let's say you've had a pendulum that you've been swinging as an experiment, and you've taken observations on the length of time that the pendulum takes to swing back and forth, and you plotted them all, and you applied different weights to the pendulum. So in theory, the amount of time it takes to swing will vary by the amount of weight or by the length of the pendulum and all that kind of stuff, the stuff that changes with pendulums. And also, we want to have a think about what we might plot our linear regression line to. What would be the best fit for those observations based on the position they are on the graph? So having a quick look at this one, there's a Slido in just a second, but I'm going to show you all three graphs. So have a look at this one and have a think in your mind whether you think that that fit line fits really well with the observations or not. And you'll get the answer. You get the chance to answer in the quiz in just a second, and then one of you will win, apparently. Have a think about that one. How do we feel about that particular fit line in terms of how it fits to the data? And then we've got this last one, which we can have a look at and see whether we think that one fits to the data. So I've got a Slido on the next slide. Let me make sure that in my other window that I've got open, I've actually got the Slido up so I can control it. Oh, bear with me. Oh, my screen sharing is paused, sorry. Here we go. Oh, I can see one person has got in already. Hopefully it's not me. Let me just...
Could you put the QR code up for a second?
Yeah, sorry, I don't know why it stopped me. Is it? Yeah, I'm screen sharing again. Sorry. Or you can join, go to Slido and put in 2290520. I'm just going to bring up the presenter mode on my other screen, and then I will come back to the slides. Sorry. I can see 4 people are in. I won't wait until absolutely categorically everyone is in, but once we've got at least 6 to 10. Got 6 people. Seven. I assume TLC is Kelly. And maybe the prize can be one of the coveted bars of chocolate. I will somehow convey it to whoever it is via the power of giving it to Kelly if the person lives in the States. Got 8. I'm going to wait until we've got 10, because then that's about half of the people who are, yeah. Okay, shall I let everyone in? So the quiz is, I'll put this back to the previous page. Oh, sorry, to this one. So you've got plot 1, plot 2, and plot 3. And then the quiz, I'll just move it forward. Which plot is correct? And even though I told it not to set a 20-second thing, it's set a 20-second thing, and which is very irritating. So oh, a couple of people left. 3, 2, 1. I'm sorry. So according to the leaderboard, everyone voted for plot 3 because you're all correct. Everyone who voted, apologies, there was one person who didn't vote quite in time. But yes, you're all correct. The answer was plot 3, which was this one. And it's obvious, right? It's really obvious that that is how you would fit that. And do you know what that means? Is congratulations. You've all just done a linear regression visually, which is very impressive. So, you know, don't discount yourself if you don't feel comfortable with statistics. You've all just done a linear regression, but you did it by squinting and looking at the graph. So, you know, there are always ways of doing stats where you can do it intuitively. And one of the things that I found very beneficial in my course is I was terrible at like the really theoretical stuff, but asked me to like plot a graph and then tell you why the data was a particular way round. I was really good at that. Or think about all the variables or confounding factors that might impact an experiment. I was really good at that kind of stuff. Like, how would you change the experimental design to make it more applicable, to analyze the different variables, that kind of thing. So just because stats feels uncomfortable to you some of the time, it might be you're just not good at that type of stats. Like some people are better at some things than others. Like my eldest brother is great at equations, super clever, but actually on some of the stuff that's more intuitive, that's more kind of you've plotted something and then you've worked it out based on observations. Maybe you're more applied and experimental than you are theoretical. So congratulations, everyone. You've just done a linear regression very quickly. And then I wanted to do like a quick reminder of like the stats underlying hypothesis testing when you do it frequentistly. Sorry for the term. So imagine you've gathered a sample which you believe comes from some specific distribution and you want to test, is the mean what you think or is it something different? So when you start taking your observations, which are your x's, you'll have a value of the mean and then you'll have an error or a difference between the deviation from the mean. And you can collect all those errors into a vector, and we assume that the distribution of all those errors is even, either side of the mean, so that then when you sum them all up, it actually makes 0, so they cancel out. So that's what you need to know about the error structure. And then you start framing a hypothesis. So the null hypothesis is the true mean is the mean 0 or mu 0, which so there's no effect, nothing interesting is happening. And then the alternative hypothesis is that the mean is not mu 0. It's not the original mean of the population. In the case of normality, you think that the errors are independently and normally distributed. So you say, we remember what we did a few minutes ago about looking at different distributions. The normal distribution is a specific distribution. This is useful because it means that the sample mean is also normally distributed. So it makes it really easy to calculate our probabilities and to do our statistical test. If it's not normal, maybe it's large, or there's some way in which it's wonky or skewed. As long as your errors have a finite mean and variance, then it's fine. And central limit theorem means that if n is large enough, the mean is approximately normal regardless of the underlying distribution. And this explains why we can use other tests like a t-test, because actually it isn't the distribution of all your data, it's the distribution of your errors around the mean. And that's actually what you're interested in. So the test statistic for this one, I chose the t-test because it was normally distributed, choosing and calculating the test statistic. So we know that we can apply the central limit theorem in this example. So the test statistic for the mean, I somewhere or other have a book right here, which has got all of my Cambridge statistical tables in it, which lets you go and get your T statistic or your Z statistic. In fact, is it here? It was here. It was in amongst these little things here, but it's gone missing. So under the null hypothesis, if all assumptions hold, Z follows a normal distribution, and you can look at the value of Z. If it's large, extremely positive, extremely negative, your sample mean is far from what you'd expect if the null hypothesis was true, and so that means you can reject the null hypothesis. So congratulations, you've just done some essential hypothesis testing. So now you've done a little linear regression and you've done some essential hypothesis testing. I'm also now going to quickly show you the example where if you were doing the same thing, but in a Bayesian kind of way. So sorry for everyone who wasn't expecting maths, but you did sign up to a statistics session. So to do a Bayesian equivalent procedure, imagine that you've run some sort of campaign where you're driving traffic to the site and you're then looking at the revenue based on some offer code that you're giving someone because they've come in from PPC. In campaign A, you've got 5 observations and that's the distribution. In campaign B, you've got 5 observations and that's the distribution. Roughly looking at them, even if you eyeball it right now, you can see 30, 29, 31, 32, 28 are probably higher than 24, 26, 25, 23, 27 on average. So you intuitively can look at that and go, I think that B might win, but let's take a look at the statistics. Is the average order value actually different between those campaigns, or is it all just random noise? In frequentist world, we would run a t-test and we'd produce a mean of 25 and a mean of 30. So magically the mean of campaign B is higher. The variance for both is 2.5 because you've got the 5 observations and stuff. And then the p-value of 0.0011. So that leads to a very strong evidence of a difference, or a very strong ability to reject the null hypothesis, which is that the mean in B is going to be the mean in A. But if I was doing this in a Bayesian way, I'd estimate the probability distribution for the difference in the means. So you'd have a posterior mean, which is the same as the observed difference, so -5 between A and B. You'd have a posterior standard error, so assuming you put a non-informative or vague prior. So we talked about priors earlier, which is where I said, if you think it's going to be a specific value, you know, or close to a specific range, you might put a prior in place. But in this instance, we didn't, because we didn't know anything about this. This was a brand new campaign. In Bayesian testing, you say credible interval. So that you've got a 95% credible interval, which means that the change in the mean is the change in the value, sorry, is -5 plus or minus 1.96. So that's the credible interval is from the true value lies between -6.96 and -3.04. So this means there's a 95% probability the true difference is between those. And so actually, you know that it's quite likely, you know, we believe that it is higher in B than in A. So you can see that you end up with like a slightly different, you end up with the same decision in both instances, but the way that you explore the difference, the decision is different. So in the frequentist one, I just wanted to know how big it was. Like, is it bigger? Yes or no? And I didn't really care about some of the other properties. Whereas the Bayesian procedure, I learned a little bit more about where the true value might lie. And actually there's, you know, you might want that credible interval to be a bit clearer so that you know that it's as clear as possible where the actual value lies. And so you learn a little bit more about where to place your next set of beliefs and what you might learn in your next experiment, but also if there was any value in any previous experimentation you've done, and there might not have been. So that's kind of the difference. Talking about prior and posterior improper priors, Claude did this diagram for me on the right, and I don't think Claude did a very good job because it's meant to show that you had a very flat prior, which is the tiny, tiny blue line at the bottom, and then the red line is the posterior. So it shows that we had a very uninformative prior when we chose this prior. And you can't see the green line because it's, well, it's, yeah, over there. So the red posterior show exactly, you know, what you're kind of trying to say with your data, was that the difference in means is around -5 with high certainty. So you can see that purple line, which is the difference in the means. And the two very sharp curves basically coincide with each other, which is why you can't see them. But essentially, we had a very flat prior, didn't inform us about much. If we'd chosen a more informative prior, maybe we would have ended up with a slightly different result. Maybe we could have had a posterior that was slightly more narrow interval, so we would have known more clearly that the result sat in a specific place, or that we would have had more confidence in the result. Pragmatic steps to choosing a prior. So my favorite one is the first one. Talk to your stakeholders. Like, you should always talk to your stakeholders in testing. But what's their kind of comfort level with risk, subjectivity? Do they want to let the data speak, or will they trust in past experiments? That's kind of the decision that I was trying to talk about earlier. Look at your historical tests. If you've got lots of past tests, summarize those effects to propose a plausible range or center for theta, or your mean that you're trying to test. Stress test your sensitivity. So run your main analysis with a few reasonable priors and try different ones. So you could do like a flat weakly informative one, or you could do a slightly stronger one and see how it affects your results. And then document your choices. So when you've actually had a stab at doing this, document what you've done. And types of choice you might make for priors. So there's what's called non-informative or flat, where literally you're not actually adding any information. Weakly informative might be sort of this shape, and then highly informative is like, I'm 90% certain it's going to be in this range, so I'm going to say with my prior distribution that it's in this range. And so overall, that's kind of I think actually this is the most useful thing to take away from Bayesian testing, Bayesian's inference, sorry, when you do specific types of testing, is that actually it's about looking at how you make decisions and how you talk to others about the decisions you're making, how you explain decisions. And it's less about the really complicated stats methods. Like it's more around having a different lens through which you can explore a decision and talk to others. And don't worry too much about that. And people are always going on about frequentist versus Bayesian. And I hate that, kind of hate that a little bit, because it distracts people from the reality, which is you need to make a decision somehow, and you've got tools in front of you that will let you do that. If you're fiddling with abstract ways of doing things, you're getting distracted from what's really important to your stakeholders, which is making a business decision, because that's what really A/B testing is about, is making decisions rather than fiddling infinitely while Rome burns, sort of thing. So congratulations, you've just done some Bayesian hypothesis testing. So look at that, in one session, you've done a linear regression, you've done some essential hypothesis testing, and then you've done some Bayesian hypothesis testing, all in one session. So there we go, congratulations. In terms of what I have for the rest of the session, I've got a quick summary. So they're just different inference schools or approaches. Most people find frequentist easier than Bayesian because it requires fewer of those complex assumptions up front. Business users often get frequentist confidence mixed up with Bayesian confidence. They think, oh, when I see 90% confident, that's how confident I can be. And honestly, it's up to you based on your confidence with stats and the time you want to apply to learn the methods. So what I'm trying to say is, don't force yourself to learn some like magical, all-seeing, all-dancing stats method if your out-of-the-box A/B testing tool gives you a reliable result. Now, you need to, the qualification there is it needs to give you a reliable result. But if your A/B testing tool gives you a reliable result and you can make decisions, great. Don't waste loads of time don't do what I did and do like a data science course and then do an applied stats course and then realize you didn't need to do either of them. So that would be my main learning for everybody else. And then just a bit of a visual difference in how you might look at these. The furthest left one is for when you're doing frequentist testing and you're looking at the means and the 95% confidence interval. The middle one is when you're doing Bayesian and you've got a posterior and you've got a particular distribution that you think is going to line. And then the far right, we didn't talk about likelihood, but that's how you plot stuff to do with likelihood on the far right, which is slightly terrifying. So don't worry about that unless you actually really want to go and learn that in a stats course. And then I've got some references here, which are quite good. which are all actually in my bookcase right now. So Roger E. Kirk, it's a tome, but it is very good if you want to learn about experimental design. Like basically my friend who, oh, now my camera has done something crazy. Maybe if I step back. That one is like an absolute tome, but it is very good. And then there's another one I've got, which is about quasi-experimental design, which I didn't talk about today, but that's an example of when you don't have a control, where you can't apply a control in a normal way and you can't do a standard A/B test. So imagine someone turns around and they're going to do a massive site-wide transformation and just turn the site over tomorrow to a new code base. Well, that's a quasi-experimental design where you've got like a pre-analysis result and a post-analysis result, but you don't have the ability to apply the control. Well, that's when you need to apply quasi-experimental design. It's used a lot in medical environments where maybe you can't choose to have a holdout group, because if you don't give people the medicine, they'll die. So you give everyone the medicine and then you measure over a specific period of time afterwards, and you take different observations, or you apply the treatment and then you remove it and then you reapply it. So it gives you lots of ideas of how to do that. That's a very good one. Bayesian approaches. Uri Bram has a really good basics of like Bayesian statistics book. It's like 100 pages maximum. And I read it like 15 years ago and I was like, this makes sense to me now. For anyone who wants something ultra nerdy, go for Bradley Efron. That's something that my stats person recommended to me. Georgi Georgiev, you guys probably know that person. Armitage et al. And SD Sylvie. It's this one. This was a great book. I found this in a secondhand bookstore somewhere in London. And it just has a really nice way of explaining different inference schools in a way that's really practical and helps you to actually understand it. So I definitely recommend that. There's some good stuff on DataCamp. And I don't know if any of you know Alex Buck. He's a product person, but his background is in physical product design. And he has a really good YouTube channel called Product Scholar. And he does statistical concepts, but from a very physical product design environment. So if you're building plastic hips or synthetic hips that need to go in someone's body, how many thousands of synthetic hips do you need to test and smash to make sure that you know none of them are going to smash when they're in someone's body? So how many of your physical products do you need to actually destroy in order to do that? So yeah, his stuff is very good. And he's got a little one about experimental design as well. So that's kind of all my references. And then I think what I've got, oh yeah, just a summary of the session really, then me, and then a thank you slide. So
Yay!
yay!
This was
And
awesome.
we have a few minutes left for questions, hopefully.
Yeah.
If anyone
Does
has some.
anybody have questions? This was awesome, Ellie. And for those of you who don't know, Ellie normally does this as a like in-person workshop, and I asked her to convert it to a webinar. And Ellie, I think it worked really well. You were all worried
It does
about
help having a Slido. It does have a Slido, which always
Yeah.
helps having a Slido to make people
Yeah.
participate. So
This was awesome. I like Tim's comment. He was already terrified by Bayesian. Thanks for introducing another level with likelihood. While people are thinking, I'm going to tell folks about what's coming up. Hold, please.
can I just quickly show my little QR code?
Oh
So if
yeah,
people
please
want
show
more.
show your thing.
Yeah. So if anyone wants more resources or would like a free coaching session with me,
Oh yes.
please scan this QR code. I'm fingers crossed I put the right QR code in, because I'm a bit
Oh,
confused
that's
about my
funny.
QR codes this week. But you can book some time with me, and then it will go to a page that has a booking button. It has a link to my LinkedIn, and then it's just got some stuff about some stuff we're doing in the UK, which are events, which I assume we've got quite a lot of people who are probably US based on the call, but when it goes out in the channel, people on Monday morning who wake up UK time will be like, aha,
That's right.
I can
Because
sign up
people
to.
ask, is it going to be
So,
recorded? That's
yeah.
right. So
Should
I
I
don't
stop sharing? And I can always
no,
give the
leave it up.
link in the
Leave it
chat.
up.
I'll
Just
say
leave it up.
something.
Really quick, and then yes, Erwin, just a second. Because I have to publish it, but we're going to have a special Halloween panel on AI shopping. It's like tricks or treats, because there's a lot of people that are really worried about the new the announcement, the birth announcement, as Sonny called it, between OpenAI and Shopify and what that means for brands. So Sonny and I are going to be the co-moderators, and Louisa and Carlos are going to be our guests. And we're going to talk about what does it mean for brands? What is it like? How do you prepare for the holiday shopping season? How can brands prepare for AI shopping? And what does it mean if people can buy on ChatGPT, basically, and elsewhere? So more on that coming soon on Halloween, 10 a.m. Central Time, and I'll get all the other times, but I'll be posting that probably today. But yes, questions.
Yeah, several of my professors informally would talk about the interocular trauma test. Have you heard of it? It's the concept is if the data hits you right between your eyes, that is, if it's just a glaring result, you can probably trust it more. Uh,
Or the opposite in my field, where we were looking at fossils that were like 2 billion, well, over 1 billion years old. And I had a Canadian professor who would say, it's not a fossil, it's not anything, it's just a poke in the eye. So that was so that's the opposite test, is like, look at a rock and can you see anything in the rock? No, there's nothing there. Just abandon all hope. Like, you've got no fossils, basically.
Thank you.
Awesome. And I don't know if you saw Tim's comment, but he said it was great. Definitely moved his intuition a solid few steps down the road. Not sure if he was walking on the left or right side, but definitely forward.
And I will find a way of sharing the slides. Because they're in a Keynote, I'll export them, and then maybe I'll put the links to the references just on a single page, or I'll pop them in the chat so that people have got them
Perfect.
as well.
Yeah, that'd be awesome. Thank you, Ellie. Thank you, everybody. Have a great weekend. I will post the recording in about an hour, however long it takes to process. Bye, all.
Bye, everyone.